Now, I know I said in previous videos that I was going to try and upload more frequently, namely one video every week. I just can't really do that. Like, I've tried, okay? It's been a long school week. I'm tired. Everyone's tired. I'm not feeling up to recording. So I'm going to try. I'm probably not going to, but I'm going to try and upload a video every 2 weeks. And the video is going to be something like this. Now, this sum, you can tackle it in a multitude of ways, but I feel like the one that I'm going to present is going to be probably the most fun and interesting one out of everything you could have done. And the star of the show is, as it usually is with math, the Riemann zeta function. This is defined as the sum is equal to 1 to infinity of the reciprocal of n to the s. Now, this sum shows up in all sorts of different places. Mainly it's calculus, summation calculus, integral calculus, but it also shows up in parts of number theory and, more importantly, the Riemann hypothesis. I'm not going to try and solve the Riemann hypothesis, just note that. But we're actually going to look at this definition and we're actually going to extend it. So we're actually going to extend it to the complex number, so zeta of x plus iy. Now, based on the immediate definition, we have to infinity of this n to the x plus iy. Remember that, okay? And basically, we're going to split this up, right? So now this is going to be the sum, and is going from 1 to infinity of 1 over n to the x times n to the negative iy. And this allows us to use properties of exponents and Euler's formula. So we would get this is equal to the sum, n is equal to 1 to infinity of 1 over n to the x of e to the iy natural log of n. And then once again, using Euler's formula, we have this is going to be the cosine of y natural log of n minus, that's going to be y minus, because technically there's a minus over here, I sine y natural log of n. And this is going to be the thing that we're going to be using for the majority of the video. And what we're going to do, we're actually going to split it up into two sums, a real and an imaginary part. So we have a sum, n equals to 1 to infinity of 1 over n to the x times the cosine of y natural log n. And this is going to be minus I times a sum, and is equal to 1 to infinity of 1 over n to the x times the sine of y natural log of n. So this is how you express the Riemann zeta function in terms of rectangular coordinates. And what we're going to do next is we're going to switch that. We're going to switch it to polar coordinates. So if you treat these as two known values instead of just functions, you can also write that the zeta of x plus iy is going to be equal to r, but r is the square root. This thing's squared, so we have, oh boy, sum, and it goes to 1 to infinity, 1 over n to the x times the cosine y natural log, and this entire thing squared. Now, this is technically plus, okay, yeah, plus, and then this is going to be minus this sum, but to square something, squaring is an even function, so that doesn't matter. We have a sum, and it's equal to 1 to infinity of 1 over n to the x sine of y natural log of n squared. This is the radius, and then we're going to have a e to the I data term. Here we have e to the I arctan. That's the formula for theta. of, oh boy, it's gonna be like b over a, right? So that's gonna be this thing over this thing, which is going to be a hefty fraction. Infinity of 1 over n to the x sine y natural log of n over some infinity of 1 over n to the x cosine of y natural log n. Right, and this is our complete expression for our zeta. It covers the entire blackboard, and that's just a feel for how long this is. But we're actually going to split it into two main parts. First off is this bit, of course, that's the ratio. And not the ratio, that is the radius. And the second is this hefty fraction. And we're going to first look at this. More importantly, we're going to look at just this squared term. So it is of the form, the sum, n is equal to 1 to infinity of a n squared. Now what we can do is we can set this as like a sort of limit as this upper n approaches to infinity of the sum. N is equal to 1 to n of a n squared. Now let's see what this thing is. So when n equals to 1, there's not much to talk about. When n equals to 2, it is like a1 plus a2 squared, which is a1 squared plus a2 squared plus 2, a1, a2. So that's not much to talk about right there. And then now for n equals to 3, we have here a1 plus a2 plus a3 squared is going to be, this is going to be another formula, a1 squared plus a2 squared plus a3 squared plus 2 a1 a3 plus 2 a2 a3 plus, oh boy, there's not enough room, 2 a1 a3. And I'm not really going to go and write the fourth term. I mean, you could, but it's just going to be incredibly long, and I don't exactly want to write it out. But basically, the pattern is that for this, it is equal to the individual terms squared plus 2 times one number from this sequence times every other number from the sequence. So basically what that means is here we have 1 and 3 multiplied together, 2 and 3 multiplied together, and 1 and 3 multiplied together. Now, if we're going to take that to the fourth, if we're going to have 4 numbers in it, it's going to be 2 times 1 and 2 plus, oh, I just realized I wrote that wrong. This is supposed to be 2 here. Anyway, it's going to be 2 times 1 times 2 plus 2 times 1 times 3 plus 2 times 1 times 4 plus 2 times 3 plus 2 times 2 plus 4, 2 times 4, and then 2 times this 3 times 4. So that's quite a hefty mouthful right there. But basically, it's just every term times everything. I mean, every other term multiplied by 2. So obviously, so this is going to be another limit, of course. We're still dealing with a limit and approaches to infinity. And this time it's going to be, alright, so the first thing you have to notice is the individual terms squared. So that's going to be a sum. And starting from 1 to n of a n squared. That's the first term. And then it's like 2 times a bunch of terms. So we have a plus 2 here. Now, we're going to set another variable. We'll keep using n, like why not? 1 up to n. Now here we can categorize this interestingly. So here we have just a n here, and then we're going to have to times that, multiply that by every single other term, but we can write it as every term greater than n, because if you want to multiply by something less than n, well, that's already counted because it counts when n was smaller. That makes probably no sense at all. So we have the sum k starting from n plus 1, because once again, the square terms are all here. So there should not be any repeats. All the way up to, I'm guessing it's going to be n, right? I realize I do have made a mistake because if you think about it, if n can go to n, k can go to n, which means there has to be 2 times this big N squared term, which shouldn't happen. So this actually should be minus 1. I feel like that's correct. And then of course we have an AK here. So that is basically the sort of formula for a sort of sum squared. It's basically just a sum of the squares themselves plus 2 times one term times, well, every other term. And we can use this. And what we can do now is we're just going to plug in infinity to all of these, and we will get, in the end, a sum, and is starting from 1 to n of this. No longer n is allowed. Again, that's not right. An squared plus 2, and the sum 1 to infinity of an sum k is equal to n plus 1 infinity of k. Okay, so I mean it's a little bit mind bending, but so far it probably shouldn't be that bad. And then what we're gonna do next is we're just gonna plug in our an as this thing right here. Now I do realize we have a second sum over here, and that has the exact same process. It's just we plug in a different sort of number. So here we have we're actually going to just write the entire radical here as r. R for radical. Yes, r for radical. So we have here r is equal to this thing first, so that would be the sum. And it's starting from 1 to infinity of this thing squared. So 1 over n to the 2x. And then we have the cosine of y, the cosine squared of y natural log of n here. And then we have this part. I might do this on the second blackboard. I mean, we still have plenty of room, I feel like, but it's gonna get crowded, like, very soon. I'm actually gonna just draw this sort of border here, so we know what we're doing here. There we go. And then it's gonna be plus 2 times the sum. And it's starting from 1 to infinity of an, which is gonna be 1 over n to the x times the cosine y natural log, and on top of the second sum, which is, I mean, I'm probably going to write it here, a second sum, which is going to be the sum k starting from n plus 1 to infinity of 1 over k to the x, and then cosine of y natural log of k. Right, so that's the second term, and then we have this second bit, which is gonna be a whole lot more stuff that, I mean, I can probably write, and this is not equal, this is plus, and then here we're going to have this n equals 1 to infinity 1 over n to the 2x sine squared y natural log, and then plus sum, 2 times the sum, and starting from 1 to infinity of of 1 over n to the x cosine of y natural log of n, and then here we have we know this is a sine. There's that sine, and then we have a second sum. Okay, is equal to n plus 1 to infinity of the exact same thing, k to the x sine of y natural log k. That is quite the expression, if I'm going to be honest. And I realize that I am running out of space, so I am going to leave this for this blackboard, and I'll see you in the next one, I hope. I mean, I could just press the wrong button and I would end this video, but then again, if I don't press it, this video is going to be really long. But never mind. See ya. And so here we have what we have so far. So I use simplified notation here. Theta is the sum of those two big sums. Don't know what that was supposed to mean. And then we have R is this thing right here. And I've combined these two sums to make it a little bit nicer and a little bit shorter a distance to write. Writing it this way also makes you see a really nice thing happening. We have cosine squared plus sine squared. And from the famous trig identity, that's just 1. So in this case, for this entire sum, all we have is just 1 over n to the 2x. And we know that is the Riemann zeta function of 2x by the initial definition. About this sum, there's still a lot to talk about this sum. But let's first get the first sum out of the way. So we know that this thing is just zeta of 2x based on that trig identity. And then for this thing, we're going to say it is equal to 2 times a certain number s. S for sum. I'm going to find the s. Now, we're actually going to combine these two sums in s. So we have here that s is equal to the sum, and is equal to 1 to infinity, of, since we can't combine it, since they're technically the same bounds, of the cosine of y natural log of n. I had the brilliant idea of writing this in the numerator instead of, having to make space for it here. I don't know why I haven't thought about that like way earlier, but I guess so. Sum k equals to n plus 1 to infinity of this sort of cosine term again, y natural log of k, and then we have here over k to the x, and then that is that sum, and then we have a plus, we have a sine of y natural log of n to the x, and then we have another sum here, k is equal to n plus 1 to infinity of the sine of y natural log of n over k to the, oh no, this is k, right, this is k to the x. So once again, quite a large sum, but I mean that's kind of what we're dealing with this right now. But it's gonna get a lot better, because what we can do is technically, in terms of k, this is just a coefficient, so we can drag that in, and then this as well, so we can drag that in, and once again, these two are the same bounds as each other, so we can combine those as well. And from there, I think we can factor out this n to the x times k to the x. And so we would get this sort of double sum sort of thing. Sum k is equal to n plus 1 to infinity. And then here we have 1 over nk to the x. And then we have this cosine of y, natural log of n, cosine of y, natural log of k. And we have, didn't we go stay here? Not really sure. I think I didn't. I hope I didn't. Sine y, natural log of n, sine y, natural log of k. Yeah, like I said, big expressions. I usually make a lot of mistakes in big expressions. But this has a rather peculiar form, and that is the form of cosine x, cosine y, plus sine x, sine y. And this is another trigonometric identity, and it's going to be equal to the cosine of x minus y, or the cosine of y minus x. And we're going to consider both of these in the next equation, but keep in mind that we sort of want the bigger number to subtract the smaller number, because we don't like negatives. I don't like negatives. So here we have, this is an entire expression just completely collapses. We have a sum n is equal to 1 to infinity of a sum k is equal to n plus 1 to infinity. This term still stays the same, it's still nk to the x. And then for this term, we have here the cosine of y, natural log of n, minus y, natural log of k. Now here we're going to do something a little bit different. We're going to switch these. And the reason we're switching them is because, well, here k is always going to be greater than n here. And so their natural log will be bigger as well. So I have a positive number. But at the same time, this is also a sort of logarithmic identity. So we have this is now equal to the sum, infinity, k is equal to n plus 1 to infinity, of 1 over nk to the x cosine of y natural log of k over x. And once you look at that, that was our original sum that we were trying to use, that we were trying to do. And now our goal is pretty much set. If we can find r, we can find the zeta of 2x plus 2 times this sum, and then from that we can then derive our original equation. And that is all we're going to do so far. And next major step is find out this theta. But I feel like I'm going to use that in the next Blackboard, since this Blackboard was just completely about finding the radical. So take a look at it, and I'll see you in the next Blackboard. And this is what we have so far. And I've used this S here. S denotes our original sum that we really want for this video. And then once again, I've written out data, and I've written these two sums extremely small because I did not have good space management. But I digress. So we're gonna set this equal to sum S1 over S2. Once again, S1 is this, S2 is this. And so we can tackle these two different sums differently. And how I'm going to do that is we're going to use Euler's formula again, but in a bit of a different taste to it. So once again, for the Euler's formula, we have e to the I times theta is equal to cosine theta plus I sine theta. Right. So now what we're gonna plug in e to the negative I theta. And so we have here e to the negative I theta. Cosine of negative theta is just cosine of positive theta. And then here we have minus I sine theta, because the sign of a negative number is negative the sign of the positive number. So what we're going to do now, and once again, our goal is the cosine. So what we want to do is we're going to add these up so that these two cancel. And so we get e to the I times theta plus e to the negative I times theta is equal to cosine, I think about it, 2 cosine theta. And then we can just move this to the other side. And boom, we have a formula for cosine. This is well known already, so I might have just wasted a lot of your time, but I wanted to get it clear for those who don't know. We have 1 over n to the x, and then we have e to the I. Theta is y natural log of n plus e to the negative I y natural log of n over 2. Now we can do 2 is a constant, drag that out. But more importantly, this is just n to the iy and n to the negative iy. And we're going to use that. So we have equals to 1/2 times the sum n is equal to 1 to infinity of 1 over n to the x times this n to the I y minus, oh no, it was plus n to the negative I y here. And then we can use the definition of the Riemann zeta function again. So we have here e is equal to 1/2 times this, I'll use parentheses, Riemann zeta of x minus iy, right? And then plus Riemann zeta of x plus iy. And this is the value of our top expression. And now for our bottom expression, it's going to be S2 is equal to a sum and is equal to 1 to infinity. And we're now going to go back to this. And what we're going to do, sorry, excuse me. That was not meant to happen, okay, ignore that. Basically what we're going to do is we're now going to subtract one from the other so that the cosine terms cancel out. So we have e to the I theta minus e to the negative I theta is equal to 2I sine theta. And once again, just like before, what you can do is you can divide by 2I. But then again, 1 over 2I is the same as negative I over 2. And so that is our second expression. Now, negative I over 2 is a constant. We can drag that out. So we have here, not supposed to have it. Negative I over 2, right? And then here we have another sum here, 1 over n to the x. E to the I y natural log of n is going to be n to the I y, okay, minus n to the negative I y. It's just the exact same thing. And then we can use the Riemann zeta function again. We have negative I over 2 times the Riemann zeta function of, we're actually going to use this negative, we're going to turn it into positive, that will switch these two around. So we have x plus iy minus zeta x minus iy. And this is what we have for our two sums. And basically all we're going to do is we're going to divide one by the other. And we can see some interesting cancellation happening with the 1/2. So we have in total data is equal to, think about it. It's 1 over S2, right? So that's going to be this thing first, 1/2 times the zeta of x. I'm going to write plus iy first because, yes, minus iy. Here we have positive I over 2, zeta x plus iy, minus zeta x minus iy. There you go. And then 1/2 cancel. 1 over I is going to be negative I. So we have negative I times this rather complicated fraction, x plus iy, plus x zeta of x minus iy over zeta of x plus iy plus minus zeta x minus iy. And that is a hefty expression for our zeta function. But we have it. There's that. There's theta. We have our radius. We have our angle. Well, we still have to take the arctangent, but that is simple as just plugging arctangent to this. And here we're actually going to go a rather long way to find out the arctangent function. But I feel like that's okay. Going the long way is fine. For once. Anyway, that's all for this blackboard, and I'll see you guys in the next one. Good to have a drink. I've been talking for a really long time. This is my second take at this video, so my throat is not doing well. But anyway, this is our main quest for this blackboard, and we can immediately do some changes. We can move this negative to the outside. But our biggest problem here is the arctangent. We don't really know how to find the arctangent. Well, maybe you know, but I don't know. So we want to find the arctangent of an imaginary value. And how we're going to do that is we're going to look at the definition of arctangent itself. Basically, if we're going to set this equals to y, so say y is equal to arctangent x, then what that means is that x would be equal to tangent y. And since we're dealing with things in the imaginary complex plane, you can use the complex version of the tangent function, which is really just kind of simple. It's just sine y over cosine. And we can use that expression we found earlier to be, this would be e to the I theta iy minus e to the negative iy, and over here over 2I over e to the iy plus e to the negative iy over just 2. Okay, and then 1/2 cancel out, and we have an I out here at the front. And then over here, what we have here is e to the iy minus e to the negative iy over e to the iy plus e to the negative iy. And here is our expression, main expression for here. Now we're going to do substitution. We're going to let, say for example, t be equal to e to the iy. And basically what that means for us is that now this is just t. These are just t's all around. And then what we have here is 1 over t, because exponents are negative, so it's 1 over that. And so we have here x. Your x is going to be equal to I times t minus 1 over t plus 1 over t. Wow, that's the simplest equation I've dealt with for a really long time. I spent like half an hour doing this, by the way. Anyway, so we can rationalize the denominator since this is a complex fraction. I have no idea what I'm talking about. Rationalizing the denominator? I'm not really sure. Anyway, it's going to be equal to t squared minus 1 over t squared plus 1. Verify it. I'm too lazy to verify it. And so basically we can do interesting stuff with it. Basically, we're going to multiply by this denominator here. So we have x times t squared plus 1 is equal to I times t squared minus 1. And now what we're going to do is we're going to subtract this from both sides. So we have x t squared. We might as well distribute plus x, and then here it's going to be minus it squared, and then minus because it's positive, so we have plus I, and this is all equal to 0. And we can manipulate this to be of quadratic form. So we have t squared times x minus I plus x plus I is equal to 0. And so we can use the quadratic formula. I'm not really sure if quadratic formulas work in imaginary numbers, but I'm gonna assume they do. And so in this case, we have t be equal to, b here is just 0, so it would just be plus minus. Although I feel like I'm gonna go with the plus root for this one. No idea why, but we're going to do it with the plus root with this one. And then we have b squared, which is nothing but 0. And then we have minus 4 times a, which is x minus I, times c, which is x plus I. And so we have a difference of squares thing going on, but I'll deal with that later. And then over 2a, which is going to be 2x minus 2I. You know what? It probably looks better if I just did 2 times x minus I. And what we're going to do next is a little bit of simplification. So once again, we have the difference of squares and the radical. But more importantly, 1 over half. And then for this 1 over x minus I, we're going to multiply by its conjugate, which is x plus I, over, and we have a difference of squares thing going on. So we have x squared minus I squared. So we have x squared minus negative 1, so we have x squared plus 1. And then we have this square root, negative 4 times, once again, difference of squares, so we have x squared minus I squared, which is going to be plus 1 over here. And then we're going to split this up, so then root negative is going to be just I. Root 4 is going to be root is just going to be 2, and then root x squared plus 1 is going to be the exact same thing. So here we have equals to 1/2 times x plus I over x squared plus 1 multiplied by I times 2 times the square root x squared plus 1. And then obviously we have cancellations, and then for this one, we can cancel this thing, and this will turn into the square root x squared plus 1. Ooh. So here we have our final value for t being equal to I times x plus I over the square root x squared plus 1. How delightful. And now we're going to use the fact that t is equal to e to the iy, so we're going to plug that in. But before that, I feel like I'm going to erase this a little bit because it went downhill a little bit and it took a lot of space, so I'm going to have to erase this, first of all. So I have here t is equal to I. Let's see if I can remember it correctly. I probably don't. I think it was x plus I over square root x squared plus 1. If I made a mistake, well, too bad. my memory is not that great. But once again, we have this is equal to e to the I times y. And for this, we want to isolate y for here. So we're going to take a natural log on both sides. So we have iy is equal to the natural log of these. So we have the natural log of I, which we'll get to in a moment. And then we have plus the natural log of x plus I. And then minus the natural log of this. Only this is the natural log of this is equal to 1/2 times the inside, which is the natural log of x squared plus 1. Oof. And this is what we get as our final expression. So here we're gonna have what should we look at first? Probably this one. This is the only thing we're gonna have to look at. So if we're gonna look at the complex plane real quick, this is going to be the complex. This is going to be real. I is over here, right? So if the origin is here, O, we can write it as rectangular coordinates. And now that distance from the origin is going to be equal to 1. And then that angle here is going to be 90 degrees or pi by 2. So here, what we have here is a natural log of 1, which doesn't change anything, times e to the I theta, which is pi by 2. Or you can verify that this is true because I is negative 1 to the 1/2, and negative 1 is e to the I pi. So there's that. And so we have this is equal to I pi over 2. Very quick, very easy. And now all we have to do left is to divide by I throughout, and we would get that y, which was our arctangent function, is equal to this I will cancel also away, pi by 2 plus I. Oh no, it'd be minus I because this is going to be plus 1 over I, and 1 over I is negative I. So we have here minus I. Oh boy, that's a lot of talking. Natural log of x plus I minus plus 1/2 natural log. Oh yeah, we have I natural log of x squared plus 1. And there you go. So this is our arctangent function. And, well, we're not interested in just the arctangent function. We're interested in the arctangent function of I times something. So we're actually going to say that this is just arctangent. So we have the arctangent of I times some number x is equal to, we just plug in ix for this. So we have here pi by 2 minus I natural log of ix plus I plus 1/2 I natural log of ix squared is going to be negative x squared. So we have 1 minus x squared. And we can factor out an I here. So this would be natural log of I, which we already know, plus natural log of x plus I, x plus 1, that is. And so here we have, this is just my pi over 2. My nose is blocked. That's probably irrelevant. So here we have what we have here. Oh boy. So this is also equal to pi by 2 minus I times I, so that's going to be plus I pi by 2. And it's going to be minus, plus, which is going to be minus I. Think about it real quick. I times I, so there shouldn't be any I here. There shouldn't be any I here. So I mean that this is just pi. Minus I times this natural log of x plus 1. And then plus 1/2 I natural log 1 minus x squared. And then of course these two we can combine to get just pi. There you have it. This is our expression that we're going to be using, and we're going to plug in our huge, massive equation for this thing. Now, before doing that, we're going to plug that in, which is going to take a really long time, I'm first going to have to close that window because there's sunlight going in, but we also have to rewrite this is equal to, this is not feel, we shouldn't be writing this. We should be writing this part. There you go. Is equal to 1 minus, let me just say this. It should be 1 plus, I think. 1 plus 2 zeta x minus iy over zeta x plus iy plus, minus zeta of x minus iy, which you can verify by rationalizing the denominators. And this is going to be useful because, well, we have something over here and we have something over here. So there's that. Alright, before I do anything, I'm going to close that window because there's sunlight. So I'll see you in the next blackboard. Alright, so I closed that window. Maybe I should turn the light on. Maybe, is that better? Did that change anything? The light really doesn't do much. Anyway, here is our sum, and we are ready to plug in our massive expression for this. And while I was thinking, we really don't really need this expression. I mean, it's fine, but we're gonna be dealing with stuff like this anyways. So, I mean, we really don't need it. Anyway, I'm scared about this part because it's so complicated. There's so many terms that are just being divided stuff. Anyway, I'm gonna set this to be L1. This to be L2. Just to, make it a bit easier. And so we have L1 is equal to the natural log of, oh boy. I'm gonna just rationalize the denominators in my head so that it's not too complicated. So we have here, it's gonna be the normal numerator, so we have zeta of x plus iy plus zeta of x minus iy And then plus 1 will just be plus this. So we have plus zeta of x plus iy minus zeta x minus iy. So once again, you can already see we're going to have like a canceling thing going on. So over zeta x plus iy. Oh boy. Minus zeta x minus iy. There you go. Let me actually think. I feel like that's a little bit wrong because make b over a. B is sine over cosine, basically. Yeah, I feel like I flipped that. I don't think it should be like that. I feel like it should be, this should be plus and then this should be minus. If anything, I feel like that. Let me think. Plus would be cosine. Plus is cosine. So we have sine over yeah. I think that works. So we're gonna have to completely change this. This is gonna be minus over here. This is gonna be plus over here. But I mean, that doesn't really change anything. I mean, it changes a little bit, but it doesn't really change anything because once again, these are negative signs, and here it's supposed to be positive. I feel like I shouldn't made any other mistakes, but obviously I probably have. Equals to the natural log of. I'm actually going to just split it apart. So here we have this plus this is going to be 2 times this. So I have natural log of 2 first of all. And this is going to be plus the natural log of the zeta function of x plus iy. Go, just like that. And then here we have minus this thing. So we have minus the natural log of the zeta of x plus iy plus the zeta of x minus iy. There you go. Alright, there's that. Alright, that's done. And so the next thing we have, although we have a limited space, is, oh boy, I'm gonna have to sit on the ground to write this. L2 is going to be equal to 1 minus x squared. 1 minus this zeta minus squared. Zeta of x minus iy minus zeta x plus iy. Should we just do it? Should we just square it? I feel like that should be better. I don't want to spend all the space. So this is zeta squared plus this zeta squared, and then we have plus 2. No, it would be minus 2 zeta x plus iy zeta x minus iy. Okay, that's the first part. Oh boy. Over. And for the bottom, I think we're just going to keep it like that. So we're going to use zeta x plus iy plus zeta of x minus iy squared. Oh boy, this one's going to spark a lot of heavy notation uses or something. This is equal to. I'm not even going to bother writing this and rationalizing. I feel like if I'm going to do anything, I'm just going to skip to the important bits. And the important bits are, after you do this, so this expression, this thing, if you write it out, it's going to be zeta squared of x plus iy plus zeta squared x minus iy plus 2 zeta x plus iy zeta x minus iy. Right. So basically, if we're going to do 1 here, 1 is just this thing over this thing. And you can write this thing over this thing out, and you can subtract. But here, I'm just going to do it right here because I really don't have the sort of space to do this. So to make things, okay, so we have zeta squared of this minus zeta squared of that. That's going to cancel. once again, this is going to be cancelled, and then so it's going to be this. And then we have this plus 2 zeta this, zeta that, minus negative, so that's going to be positive 2 zeta this, zeta that. And so in the end, we just get 4 zeta this, zeta this, zeta that, over zeta this plus zeta that squared. That's going to be such a mouthful. We have the natural log. And here, I'm just going to spare like before. I don't want to write this entire thing out again. So here, natural log of 4, but that can be rewritten as 2 natural log of 2. Like that. And then here, oh boy, is equal to going to be plus zeta. Oh no, not theta. Natural log. I'm not sure if you can see. My hair is just poking up. That's all that you can see. Zeta of x plus iy. Oh boy. Plus zeta, natural log of zeta of x minus iy. And then minus 2 natural log zeta x plus iy plus zeta x minus iy. Oh boy. Oh, I can stand up again. Oh god. Yeah, so as you can see, there's our 2 values for L1 and L2. And now all we have to do is we're just gonna sort of plug that in. We're gonna have take their sum. And then hopefully after that we're gonna do some simplifications, and then hopefully we are done with this angle. This angle has taken way too long. Way too long. How long is this recording right now? We've recorded for 52. I don't think that's 52 minutes. I feel like that should be much less than 52 minutes. But I digress. Alright, well that's it. Next blackboard it is. Stay hydrated, people. Alright, so after that water break, I took time to painstakingly write these 2 equations out. And my marker is getting this sort of thick marker pen here, which means it's slowly running out. I've written a lot. But hopefully that doesn't get in our way, because we still have a long way to go. See here, we have our original angle. This is what we were looking for. And it is now equal to this thing. Oh boy, how delightful. We're going to do a lot of calculations. I swear, it's going to get a lot better. So what this is equals to, and I want to write up here, so equals to negative pi minus I guess we're just going to have to write these out. So we have I natural log of 2 minus I natural log of zeta of x plus iy. Minus is going to be plus I natural log of zeta x plus iy, oh boy, plus zeta of x minus iy. It's going to be the first term. Alright, so for this now, I don't think I need this anymore because we already have that entire expression written now. So I'm going to erase this just for some room. And then plus 1/2 I times this is going to be equal to, oh no, it's not going to be that. So here it's actually going to be plus I natural log of 2. Alright, there's our first cancellation, oh boy. And then we have plus 1/2 I natural log of zeta of x plus iy. Boy. Oh, Jesus Christ. And then we have plus 1/2 I natural log of zeta x minus iy. And then lastly, it's going to be plus, and it's going to be minus, so that's going to be a minus I natural log of zeta of x plus iy minus zeta of x minus iy here. All right. That entire thing is written out, and then here we have this massive thing canceling out with this massive thing. So, like I said, there is a lot of very neat cancellations that just starts to happen. And then minus I and this, they can be combined. So here we have plus 1/2 I natural log of zeta x minus iy minus it's only 1/2 I natural log of zeta x plus iy. Oh boy. So we went through all that work only to get just this small expression, which I feel like you would be better off just guessing what it is, other than going through that entire load of effort to finally get to this answer. But in this channel, we like to be exact with our solutions, so this is what I insist on. Now we can do some minor simplifications. So we can bring these two together. Well, it goes to 1/2 I natural log of this over that. So we have zeta of x minus iy over zeta x plus iy. Oh boy. And here we have, that is all. Whew. And we are basically done. This is incredible. We have our angle here. And if you want to recap our zeta function of x plus iy, looks kind of like this. It's going to be the square root of zeta of 2x. Remember that's from the radical blackboard we did, plus 2 times our original sum s, e to the I times this thing. Now, what is amazing about this is I and I are going to multiply together to just get -1, -1/2. And then here we have the natural log of the zeta over zeta thing. Oh my. Yeah, I mean, I can definitely see my marker starting to lose its marker thing. But we are basically done. This is the closest we will ever get. All we're gonna have to do now is we're gonna realize that this is a sort of natural log property you can use. And here, we're gonna use this negative, and we're going to just switch out the places. And then I'm going to use this 1/2. E to the 1/2 natural log of something is just the square root of something. So, oh boy. We have the square root zeta x plus iy. That was not supposed to happen. Over zeta x minus iy. And we can divide by the square root of zeta x plus iy. So over here, all we get is just 1. And then over here, it's going to be a square root. Now we can divide by this on both sides. And we're going to divide by this. Well, maybe we're going to do that in a future step. So we're just going to divide both sides by this. So we have 1 is equal to square root of zeta of 2x plus 2s. And then we have square root of 1 over zeta of x plus iy, zeta of x minus iy, 1 over that. We have the square root. Now, what we're going to do is we're going to realize that we can move this to the top. So we have 1 equals the square root of this thing over that. But at the same time, that would imply, since, 1 is positive, that would imply that this over that is equal to 1. Or, which means that this is equal to that. And, how closer would you need? So, what we're going to do, we're just going to subtract zeta of 2x. So we have 2s is equal to zeta of x plus iy, zeta of x plus iy, minus iy, I meant, And then we have minus zeta of 2x. I'm pretty much done. We can divide by 2 on both sides. We have 1/2 here and then 1/2 here. Now, we can make it better, and we can do that by realizing that x minus iy is just x plus iy, the conjugate of that. And here is going to be a little property. The zeta of the conjugate is equal to the conjugate of the zeta. Now, this can be easily proven with our sine and cosine sum. Well, I mean, to be honest, I've spent way too long recording this, so I feel like I'm going to leave the proof of that as an exercise to the viewer. And here, we can realize that we have this sort of form, z times z conjugate. And another exercise for the viewer is going to prove that this is equal to the absolute value of z squared. So yeah, I'm going to leave 2 exercises, but that's only because I'm lazy and I don't want to spend even more time recording this, because I've already spent this like for an entire hour. So basically, in the very end, we have our final solution, 1/2 the absolute value of the zeta of x plus iy squared minus 1/2 zeta of 2x. And what a delightful ending. This is over 1 hour of work. At least that's what my camera is saying. It's saying 1 hour of work just to arrive at this series. And this is just genuinely awesome. I've never been more excited to share like a video in our lives. And I know that, you know, this has made me extremely tired, but I feel really good. I feel really good. It's been such a journey. It's been such a journey. And I hope you guys enjoyed it too. Like, oh boy, what a journey! I mean, the sum doesn't even look that complicated. I mean, the last video I did was about a way more complicated sum with floors and all of that, which you should check out, by the way. It's just the last video I did. But that one only took something like 18, 20, 30 minutes. This one took an entire hour. Oh boy. But that's it. Alright. Hopefully I'll be able to record another video in another 2 weeks, although I probably won't be able to. I don't want to raise you guys' hopes too much. Well, that's it. See you in another 2 weeks. And just remember that no matter how difficult a problem solves, it's probably going to take a really long time, even if it's definitely possible. I don't know why I decided to do like a sort of a motivational quote at the end, but yeah, see you guys. Bye.